Now that we have our opcode caching set up from our previous part, we can finally get to writing the rest of our opcodes for our Chip8 emulator so we can have a complete functioning CPU. We're going to start where we left off. The last opcode that we had implemented was 7000, which up here was just adds KK to VX with no carry. And now we're going to start from 8000. So 8000 has quite a few opcodes here, so we're going to need to make another statement to switch between them. Let's go ahead and do that now. So if you remember from our previous part, we made a variable in our CPU opcode caching structure that took the least significant bit and set it aside. We can use that bit to differentiate between which 8000 opcode we are currently on. So we're going to make a switch statement based on that. And the variable is just the single n that we added to the structure before. And just to do a quick recap, this was our typedef structure cached OP that we made in our last part, and the value I'm referring to here is this value, which is uint8n. So before, what we did is we took each value and we separated them apart. So this one is going to be the least significant bit. This is the two next bits, including this one, and then these are the other three. We left the most significant bit alone because that's the one that we use to differentiate which instruction pattern we're on. Our first case is going to just be 0. And the first opcode just stores VY into VX, so it's pretty simple. We just take the value of the register at X and set it equal to the value of the register at Y. So V is our register, and X is the register count that we're going to be taking. We're just setting it equal. And then from there we can break. We can set this into an indented case if you want. I'm just going to put it all on a single line because these next few opcodes are pretty simplistic and they follow the same pattern. The next one is setting VX to VX or VY. So we can do the same thing here. We can get the register at X. And we can set it to or equals CPU at V at Y. There we go. Next one is going to be 2. And this one is a VX and equals VY. So same deal. This time it's and equals. And the last one is going to be an XOR. So these are the 4 first opcodes in the 8000s case, and they're pretty straightforward. They all follow the same type of pattern here. The only difference is what we're actually doing with setting it equal. So first one, we are setting it equal. Second one, we're doing an or equals. Third one, we're doing an and equals. And the fourth one, we're doing a XOR. So our next instruction adds VY to VX, but it does set our carry flag to 1. So before we go any further, I'm going to make a quick define on the top of the file. I'm just going to call it flag register. And the flag register is located at 0x0f. So every time we use this flag register keyword, we know that the actual flag register is at this location. This will make it much easier for us to read rather than typing 0x0f every time. Let's go ahead and make a case for our next opcode here. It's going to be a 4 this time. We're going to make a new variable here. We'll make it an unsigned 16-bit integer. Let's call it sum. And what we're going to be doing is we're going to be taking the register at X. We're going to be adding it to the register at Y. And then from there we can store it back into X. but we do need to add a mask to this. And the reason why we're adding a mask is because if the sum were to go higher than the 8-bit value, it would then wrap into a 16-bit value. And to prevent that from happening, we're just going to mask it off as an 8-bit value so nothing gets messed up in our code in the event that the addition does go over the 8-bit limit. Now we need to set our carry flag. The carry register is also going to be in V, but we can just say flag register as our location. And we can now check if the sum was larger than the 8-bit value. What we're going to do now is we're going to take our sum and we're going to check to see if it's larger than 8 bits. If it is, we're going to set it to 1. If it is not, we're going to set it to 0. That's pretty much all we need to do with the flag register. If we needed a carry, then we would set it to 1. If we don't, then we just set it to 0. Our next opcode is going to be a subtraction this time. So what we're going to need to do is we're going to need to keep a temporary variable for before our subtraction so we can tell if we needed to set the borrow flag or not. And the reason we would need to do that is if the subtraction wrapped around. And to start, we'll go ahead and make an 8-bit value to hold the original. We'll call it VX old. We're just going to take the value of the register at X and store it in this temporary variable. From there, we can do our arithmetic. Make a 16-bit unsigned integer. Call it diff for difference. Take our old value and we'll subtract it by the value in the Y register. From there, we can set the register at X equal to our difference. Make sure to mask it off. And now we need to set our flag if it wrapped around. So we can check the VX old, and we can see if it is greater than or equal to the actual value that we subtracted from. So the way that this works is if the original value was greater than or equal to the value that we used to subtract out of, then we did not need a borrow. We need to set the flag register based off if we did not have a borrow. So if it is greater than or equal to, then we know we didn't have to borrow anything. So we can set the flag register equal to 1. If it is not, then we know that the subtracting value was larger, which means it would have had to wrap around, which means we would have needed to borrow. So for this next one, it's actually a pretty simple bit shift. Going to be 6 this time. And we will need to make another temporary variable for this again because we are going to need to set the flag register to whatever the least significant bit was before the shift. So we'll make this 8-bit unsigned integer. We'll just call it LSB for least significant bit. We will take the value at register X and we'll mask the least significant bit out of it, and then we can save it for later. Now we can take register at X and we can bit shift it to the right by 1 and set it equal. Last thing we need to do is we just need to set the flag register, and we just set it equal to the least significant bit before the shift, and then we can break. So this next case is actually pretty similar to the 5 case, but instead of subtracting Y from VX old, we're going to be doing it the opposite way around. So we'll make our temporary variable just like we did before. Set it equal to the register at X. We will take a register at X. We will set it equal to the register at Y minus VX old. And the flag register logic is very similar here. This time we're taking the Y value first. And we're doing a check for VX old. If we need to set the borrow, 1. didn't, then we set it to 0. Now our last case for the 8 opcodes is going to be E, and this one is very similar to our 6 case. Instead, we're going to be bit shifting it to the left. Instead of the least significant bit, we actually need the most significant bit this time, so we'll call it MSB. We can mask it off using 0x80, but because we're doing it this way, we need to bit shift the value that we get all the way to the right side, so make sure to shift it to the right by 7. If you do it by 8, it's just going to go off of the bit entirely, so make sure to only do it by 7. We can take the register at X, and we can bit shift it to the left and set it equal by 1. Set the flag register to our most significant bit. And just like that, we are done with our 8,000th case. We can make sure to add a break for this switch here, so we can move on to our next opcodes. Our next opcode is going to be 9,000. And there's only one of these. And all this does is it checks the register at X with the register at Y, and if they do not equal each other, we just skip the next instruction. So we can do a if statement here. We can say if CPU register at X does not equal the register at Y, then we can increment the program counter to skip the next instruction. Take the program counter, plus equals 2, and then we can break. The next instruction is going to be at A. And this one just sets the index register to the N value. And since we already got that N value within our cached opcode structure, we can just throw it in there. So take the index register of the CPU and just set it equal to that N value. And that's all you need to do. The next opcode starts with a B, and this is actually a jump instruction. So what we can do is we can take the program counter, and what we'll do is we'll take the register at 0, and we will add our N value to it. And that's all you need to do for this instruction. We're just jumping to the value at register 0 plus the N value that we got from the opcode. Our next instruction requires us to generate a random number, so we're going to be making a helper function down here. I'm just going to call it random number. Return type of an unsigned 8 integer. The logic's pretty simple. We really just need an 8-bit unsigned integer. We can take our random function call and we can have a modulo of 256. So the random number will be in the range of an 8-bit value, and then we can return this. Make sure to include this in your header file so we can see it. And then in our main function, we need to go ahead and add this to make sure that it works. And we'll need to include the header file for this. Back in our cpu.c file, we can go ahead and declare our case for the C opcode. And what we need to do here is we need to take the register at X. We need to set it equal to a random number that we can get from our function, and AND it with the N function out of the opcode. That's all we need to do for that instruction. The next instruction is responsible for our actual video rendering, but we're not going to implement this yet because I'm going to have a separate part where I just go over setting up video. So we're going to go ahead and leave this case blank for now. Don't worry, once we get to this part, we're going to be talking about implementing all of this into SDL2. So this will be our instruction where we actually place our functions in for handling the video rendering. We can, however, add some logic to handle our inputs, which is going to be the E instructions. There are 2 cases that we need to handle for that, so we'll go ahead and make one case for E and then a switch statement within it. Our switch statement will take the KK value and we'll use that to differentiate between the two instructions. First one we'll do is case 9E. And what this instruction does is if there is a key pressed at the register at X, then we skip the next instruction. So we can do an if statement here. Take our keyboard and we'll check the register. Now we could leave it like this, but what I want to do is just to be on the safe side, we're going to mask it off. So we're going to add a 0xF mask here. And the reason I'm doing 0xF is because we have 16 keys on the keyboard. So if we mask it with the F, it can only go from 0 to 15. So we only have 16 possible cases. This may not be necessary, but I think it's a good safety measure that I'm going to leave here just in case. So if this is true, we are going to increment the program counter by 2, skipping the next instruction, and then we break. The second E case is going to be A1. This is the same thing but the opposite. So if it's not pressed. And that's it for the E instructions. Be sure to add a break here. And now we can move on to the largest section, which are the F opcodes. We're also going to be making a switch statement here. It's going to be the exact same value as it was before. Our first case is going to be 07. And this instruction just sets the register at the X value to the value in the delay timer. We take our register at X, like we usually do. And we can set it equal to the delay timer. Next case is 0x0A. And this one handles our pausing or halt until pressed function. So we need to take the values that we made before. We made a halt until pressed variable. I'm going to set that to true. And we're going to take the wait register value and we're going to set that equal to the X value. That way we know where to start back up from. Next case is going to be 15. And this time we're doing the opposite of case 7, where we're setting the delay timer to the value of register at X. Next is case 18. This time we're doing the same thing but with the sound timer. Next case is 0x1E. This one's almost the same thing, except we're doing an add equals rather than just flat out setting it to equals. So we're doing it at the index register this time, plus equals register at X. The next case is 29. And this one takes the actual font set location and puts it in the index register. So, take the index register. We'll take the font set location constant that we made in one of our previous parts. And we'll add the value of register at X. But we're also going to multiply it by 5. And the reason why we're multiplying it by 5 is because each character is 5 bytes long. So if we were not to multiply it, we wouldn't get the entire character. We need to multiply it by 5 to get all 5 of those bytes. Also, I realized I forgot a break statement here. Make sure every single case has a break, otherwise you're going to run into lots of problems when the code doesn't stop. Our next case is 33. And this one's a little tricky because we need to convert the value that we get to a binary coded decimal representation. So in order to do this, this is the way that I'm used to doing it. You take an 8-bit value. We'll go ahead and grab our CPU register at X. What we need to do is we need to store our representation in memory. So the way that we're going to do this is we're going to take our memory array. We need to do it at the index. First, we're going to do it in the hundredths place. You're going to take our value and divide it by 100. Our second is going to be the tens place. And we need to add 1 to the index so we're not overwriting the previous one. We could do our value divided by 10 modulo of 10. And then for the ones place, we can do value modulo 10. So a quick explanation on how this works so there's no confusion. The first line here is basically just taking the hundredths place and putting it into 1 byte in memory. This one is taking the tens place and this one is taking the ones place. And the way this works is, let's say you have the number 200. If I divide 200 by 100, the value is 2. So we're taking that 2 in the hundredths place and putting it in its own byte. Here we're taking the value and we're using a divide by 10 to chop off the ones place, and then the modulo gives us what's left in the actual tens digit. And now for the final one, we're just taking value modulo by 10, which gives us our ones place. And we're storing each of these in 3 separate bytes because that's the way that binary coded decimal is represented. Our next case is going to be 55. What this instruction does is it stores the register starting from V0 through the value at Vx in the memory starting at the index register. The first thing we need to do is we need to get the count of the registers that we're going to be copying over. So I'm going to make it a size T here. Call it N. Cast this to size T and we'll check the X value and add 1 to it. Next, we should check the available memory that we have. So we'll do size T available. That's 1000 minus size T CPU at our index. What we're basically doing is we're taking the maximum amount of memory that we have available, which is going to be 1000 in hex. And then from there, we're subtracting where the index is so we know how much memory we have left to write. And here we can clamp our write size to whatever will actually fit, just in case it is larger than what we have available. And then from here, we'll do a memcopy, which is why we are using size T, because memcopy likes to accept size T primarily. I think we can use a 16-bit integer, but I'm not quite sure. I always use size T here just for safety. Take the address of memory at index. We'll take the address of the register at 0. And then we'll take N. So we're taking our value N, which we just clamped, and allowing that to be our max size that we're transferring over. And then from there, we're taking our registers and we're storing them in the memory starting at our index. From there, we'll increment our index. And then we'll break. When I originally did this, I did it as a for loop, and that is also a valid way of doing it. I've just learned that memcopy, memset, things like that tend to be faster and more efficient, so I've been trying to use these methods a little bit more. I know it can be a bit tricky at first, but once you get it down, it starts to click and make a little bit more sense. And for our final opcode, it's actually very similar. The only difference is we're swapping around the values in the memcopy. First thing we do is we get the size that we need to transfer over. Now we find what's available. We then check if n is larger than available in case we need to clamp our size down. And then our mem copy. But this time we're going to do it opposite. Do the address of v0 to the memory. Then we increment our index register as needed. And then we break. And to finish this off, we need a break right here to stop our switch statement. And we are done with our execute opcode function. This was a really long part, but I think that this is the most complicated portion of actually writing this CPU emulator, just because we have to handle every single possible case that we have. The only thing we haven't done yet is the actual video instruction, but that will come when we actually look at the SDL code, and that will most likely be the next part of this Chip8 emulator, but I am happy to see that we made it this far. If things seem a bit confusing, please ask questions. I'm always here to help out as much as I can. There's also tons of resources online about Chip8s and everything else, so if things seem a bit confusing, don't be afraid to look up what you can or ask anybody any questions you have. Appreciate you guys coming. Hope to see you on the next part.